Start. Hello, everyone. My name's John McLennan. I'll fill in for Rob this morning. I'll do the best that I can. Those are big shoes to fill. And Rob asked me to sort of give an update of what's going on recently at the project in terms of field work that's going on. And so a little bit of old, a little bit of new. And so as you all recall, we've drilled 16A 7832. Last April, we did 3 hydraulic fractures in 16A. And this year we just completed drilling 16B 7832, intersecting to the best of our ability the microseismic cloud from those 3 wells. And in a commercial situation, as you know, we would populate the rest of the well. Our future plans will be to create these hydraulic fractures along 16A and also eventually do some work on 16B. And we all know that the commercial agenda for this is circulation through a heat exchange network formed by the hydraulic fractures. And the basis for success of this is independent surface area created by the fractures. So as we were drilling 16B, which was a well that was drilled 300 feet vertically above well 16A with the same trajectory, temperature was again a challenge. And so to put the geometry in perspective, here's an aerial view showing the vertical projection, or the projection on a horizontal plane of 16A, drilled at north 105 east, or 105 degrees east of north at least. And the well that we just completed, 16B, which was nominally 300 feet above, and at the toe we were maybe 70 feet north of being immediately above. So 300 feet above and a little bit to the north. And this is just sort of a little bit of a travelogue describing what was encountered in these wells. And so you all recall the temperature is going to be the dominant challenge, a conductive thermal regime with static bottom hole temperature somewhere in the neighborhood of 450 degrees Fahrenheit at the depths that we're talking about. Now, to deal with some of these temperatures, we've taken advantage of these wells and we've tried out some technologies. And one of the things that we did try out was an insulated drill pipe that was provided to us courtesy of Ever. And here's a photograph of some of that drill pipe. We did 2 runs, two bit runs with this insulated drill pipe. And in fact, the results were relatively favorable, as you can see from the next slide. So what this slide shows is, first of all, it shows orange dots. So the orange dots are measured bottom hole temperature from MWD devices that were downhole. And the blue curves are thermal simulations that were fit to these measured data. So you have a pretty well calibrated thermal model. Now, if you look to the BHA 11 and BHA 12, this is where we ran the insulated drill pipe. The model prediction was for temperatures shown at 200 degrees C plus. And the measured temperatures with the insulated drill pipe were somewhat on the order of 50 degrees C, less than that. So this is a pretty optimistic and positive finding. It's undecided whether or not the reduction in temperature assisted in the rate of penetration, but unquestionably this is something that will assist in running tools and that are temperature sensitive. So really, I think it qualifies as a significant success, and it's something that bears a future evaluation. And the DOE earns a significant amount of credit for facilitating this particular test. Now, so temperature is always an issue. The second challenge in these reservoirs, not so much a challenge, is the lithology, that we just have to appreciate what sort of lithology and naturally fractured regime that we're dealing with. And so, as we know, we're dealing with a high strength, high modulus, abrasive granitoid to gneiss. And through this and through these operations, we spent a lot of effort in terms of coring to recover core for the R&D programs and for also characterizing rock mass properties and fracture properties as well. And then also at Forge, we have a substantial interest in understanding the bit as a laboratory, using the bit as a laboratory, taking measured properties at the bit and back analyzing those properties to come up with mechanical properties along the entire length of the well. And so a lot of coring, a lot of effort in terms of reservoir characterization to determine fractures. And many of you people have seen me show this slide before, but I think it's so important. At the right, excuse me, is what we often see in an unconventional setting, where we see relatively planar fractures. What you're seeing are microseismic networks from multiple stages. And if you can look at the top panel top part of the right-hand panel, you can see that these are relatively planar. The question still remains, are these planar in a setting such as at the left, which is an outcrop of the Forge Reservoir, where despite exhumation and exfoliation and et cetera, there's indication that in situ there are multiple fracture patterns. These fracture patterns, we've been able to monitor these particularly well. Schlumberger has been a great partner in terms of doing this. And to overcome the temperature, we've done a couple of things. First of all, what you can see on the left are FMI tracks, static and dynamic FMI tracks, and static and dynamic UBI tracks. And these have been particularly illustrative in terms of determining fractures and also in terms of determining the profile of the well. The reason that we've been able to be successful and overcome temperature limitations is for a couple of reasons. And one is for a tool that's shown at the upper right. And this is a bogey. And as you can see, it has wheels. It's like a three-dimensional skateboard. And with weights and logging tools, this can be run to pretty much TD in our wells. And our wells are drilled at 65 degrees to the vertical. And that actually came about by a recommendation from Doug Blankenship. Many years ago, we were originally going to drill 90 degrees, but Doug advised us to back off to say something like 65, which is about the limit for running logging tools by gravity alone. And gravity alone is only possible with these mechanical devices, and it worked extremely well. Now, below that, for deeper, hotter, longer exposure times, we've found through bit logging technology has worked particularly well. So what you can see is you can see an open-faced bit that you run in the hole, and you can be circulating while you're running this bit in the hole. So some degree of cooling is possible. After you're at TD, or for logging, that is TD, logging TD, you pump down your logging tools. And those logging tools extend out through the bit and they latch. There's a wet couple that's decoupled, and then you back out of the hole and log on memory. Worked extremely well in all of our cases. And so substantial and excellent logging information has been derived. We've also, as I said, done a significant amount of coring. The picture at the top is from core 1, I believe. I think this is probably the first core that we took, and I'll show you that in the next slide. And there was a lot of exploration in terms of improving coring performance. And ultimately, we worked significantly with Canamera Coring, and they guided us on the optimization of the weight on the bit to optimize and maximize the length of coring that was possible for each core run. And so in terms of that, we selected 4 zones for coring. And as you can see, a shallow vertical zone, and the vertical zone was picked shallow so that we could sample some relatively newer lithologies, not newer, but ones that we hadn't cored before, and sort of start to debug the coring process, because it's a hard, difficult rock to core. And then subsequently, we picked 3 zones where we felt that the microseismic cloud from the 3 fracs in the 16A well would intersect the projected trajectory of the well that we are drilling. And so you can see, and we bracketed 60-foot zones and cored within them. Stage 3 somewhere in the 9,800-foot domain. Stage 2 somewhere in the 10,250 to 10,300 foot domain, and then stage 1, the first frac in 16A at 10,430 to say 10,490, something like that. So as you can see, 176 feet of core captured. About 154 feet of that was recovered, and that's out of a total of what, 9 runs, so 270 feet of barrels that had been run. So really an extremely successful coring campaign, and I encourage people, and right now Clay Jones and colleagues are evaluating these cores. And there'll be more to come on that. Mapping of the cores, of fractures, mechanical properties testing, determination, possible determination whether or not we detected tracers on these cores. And so a lot going on with the core analysis, and so stay tuned for that. Of course, we're always interested in drilling technology, and we had a great partnership with the bit and companies, with the bit companies in particular. Here it was NOV and Baker Hughes, and excellent assistance from Scientific Drilling. And in particular, I really want to acknowledge the assistance that we received from our colleagues at Texas A&M, and that's Fred DePriest and Sam Neuner. So there's a picture of the rig with casing laid out, and the drilling performance continued, and improvements, well, maintaining drilling performance at least continued, and the success in the drilling performance, going from the roller cone bits in 5832 to PDC bits in all of the subsequent wells, is really substantial, and is one of the success stories at Forge here. So what you can see on this plot is the measured depth versus the number of hours on bottom. That's when your bit was actually touching the formation. It's taking away logging time, tripping time, downtime, whatever. And so you can see that from 5832, which was 7,536 feet deep, to 16B, 7832, which was 10,947 feet deep, at a 65-degree angle, there's been a substantial and significant performance, partially based on bit performance and partially based on discipline for looking at dysfunctions and limiters and trying to eliminate those on the fly. And a lot of credit there to our colleagues at Texas A&M for helping us do that. One of the things that we tried to do here, and this is intentionally illegible because we don't have the time to go into it, is that these wells served as a platform for testing different bit technologies, different BHA technologies, different stabilization technologies, etc. And so it was, once again, it was a disciplined and pre-designed bit program where we would drill 500 feet with a particular bit or a particular assembly, and then pull that assembly, even if it was green. And all of the bits, pretty much all of, I think almost all of the bits, particularly the 8 3/4 inch bits, and the 9.5 inch bits, that is, were monitored with sensors, either in the bit or in the center line. And almost all assemblies also had sensors for measuring three-dimensional 3D vibrations in the BHA. So there's a lot of analysis that's going on there. And this is a particularly interesting topic because vibrations were a significant issue at, and always have been a significant issue in these drilling activities. And one of the things that we also tried on this well was rotary steerables. These are reconstructions of wellbore diameters from ultrasonic borehole imagers made in the 16A well, drilled with, I think, 1.5 degree bent motors. I think 1.5 degree. But nevertheless, what you've got is you've got here an 8 3/4 inch diameter hole in this case. And each one of these sections is about 10 feet long. And so what you can see is that going from rotating to sliding and vice versa, there are significant ledges. There's significant spiraling in this. And one of the goals here was to eliminate this rugosity, as we'll borrow a term and call it rugosity. And we tried to get around that by using rotary steerable technology. Rotary steerable technology really did improve the hole quality, and you can see that from this example. 9.5 inch diameter hole reconstructed from circumferential UBI measurements. Each one of these sections, I think, is about, I think they're 10 feet long, but you know, regardless, you can see a very smooth hole. Now, the rotary steerable certainly helped, but it did have its own issues, particularly in terms of vibrations and stabilization and temperature tolerance. And so, in never a perfect world, and we'll work ahead towards this. To help with the stabilization, we used roller reamers, and you can see roller reamers in the top here. And so what you've got is a full diameter device with roller inserts with nubs on it that help to avoid stick slip, and they worked extremely well. We had some other HFTO suppression devices on location, but HF, high frequency torsional oscillations, did not turn out to be a significant problem on this well, but they could be in the future, and we're still interested in evaluating this. And we appreciate the vendors that provided the tools, even though we didn't necessarily use them. One of the things that turned out that was problematic with the rotary steerable was the degree of vibrations. We tried to minimize stick slip by running roller reamers, but placement of roller reamers and stabilizers turned out to be a problem, and led to vibrations that were in some cases very significant. And it's something that we need to address in future drilling. So, for example, if we look at this plot, let's just look at some vibrations. And so here are some measured downhole lateral vibrations. You can see pointing to that curve as we're drilling. And here are some axial vibrations. And you say, well, what's the big deal? Well, the big deal is that this scale is 20 G. So that's 20 times the acceleration of gravity. And so we're having vibrations that were somewhere in the neighborhood of 10 to 15 G. And that's extremely damaging when you think of force times or mass times acceleration and what that can do to a tool. And so even though we had straight hole, there's work yet to be done in terms of optimizing the bottom hole assembly and the spacing of stabilizers and various devices. But nevertheless, at least I'm optimistic that this technology worked extremely well. There were complications. You can see a stabilizer at the left that has been worn down significantly, and a roller reamer. This was from a rotary steerable device that was run with a motor, and the vibrations there were very excessive, and you can see a significant amount of damage on this one. Once the motor was taken off, the RPMs were less, and naturally the damage was less. So we moved after this first run, we took the motor off, and there were improvements, as well as some changes made in stabilizer positions. And so there's a real possibility for designing and these things in advance, and improving performance. The other thing that we tried out, and this is the ultimate purpose of these forge wells, is evaluating technologies. We had a very collaborative relationship with Reed Hycalog and Particle Drilling Technologies to test out some of their particle drilling methodologies. And one of the reasons that this is particularly attractive, you can see, is from the characteristics of the bit that's shown on the right. So the principle is to inject steel shot in the drilling fluid that cuts out a central hole, and the shot goes through the nozzles, it erodes the rock, and then the cutters on the gauge create a very nice smooth hole. And just to illustrate this, you can see an animation of the particle jetting on the right. And you can see on the left from a laboratory demonstration that was cut open later on, you can see the jetting action that's occurred and the erosive action. And you can also see the very, very good quality hole that was created. Some issues in terms of bit design and ruggedness that particle drilling and NOV are working on to overcome. And so we'll hear more about this in the future. One of the other successes, so drilling was quite successful. We also ran 3 fiber optic strings, and a great deal of thanks goes out to the participants in this under the DOE R&D programs. One program between University of Texas at Austin and Shell, and another program between Rice University and Silixa. So the 3 fibers were, one was a Baker Hughes pressure temperature gauge, and that was run just past the heel, and then Silixa and Shell, well, the UT Shell team ran other fibers right to the toe of which to the shoe of the 7-inch casing. And so you can see at the right the Shell cabling, and I'm calling it Shell cabling, that's in quotes, but Shell was intimately involved. I didn't have a picture immediately of the Silixa cabling. Apologies to Silixa folks, but you can see that this was run right to the 7-inch shoe, and just sort of a few a montage of some of the things that were going on. Upper left, you can see centralizers that were specifically designed. The 9.5-inch hole is an odd-sized hole in North America, and it was designed specifically based around the fiber installation. It was the minimum size hole that we could drill that the fiber folks felt comfortable with. You can see moving casing in the bottom left, and you can see wellhead installations along the top, as well as strapping on protectors to protect the casing, protect the fiber going into the hole. A couple of close-ups of what's going on here. You can see some of the strapping of protectors at the left-hand side, and putting a master valve on the wellhead on the right-hand side after the cables had all been successfully run. And so we do have some preliminary results here. I'm going to show some work that's been provided, some analysis that's been provided to us by Nubrix Energy Services, and we're very grateful to them for their efforts, showing some of the work that was run while the cement was being circulated. I think so much. It's all very preliminary in terms of analysis and determination, but you're seeing a rate of change of strain, blue becoming more compressive, and or negative becoming more compressive, and positive becoming more tensile, and a lot of this rate change is a function of cool down and exothermic and effects at the other end, and ultimately warm back. So a lot going on yet, but just outstanding data that has been so far acquired by Nubrix and by Silixa. Now, so we've got these 2 wells in place, and our ultimate goal is to connect the wells. So I'm going to go back and I'm going to walk down memory lane for a second here and talk about the fracturing that was done at the toe of 16A so that we can appreciate the circulation testing that was carried out to determine how much interconnection there was between the wells. So let's recall, early April 2022, that is, all there was a 16A well, okay? And it had not been fractured. Later in that month, we carried out 3 fracturing stages on that well. And during those fracturing stages, we had geophones in 3 wells, and we also had equipment in 78. We also had some fiber optics in 78, and yeah. And so we carried out 3 fracture stimulations in 16B. So this is the profile of the 16B well. Excuse me, 16A well. The first was in the 200-foot open hole. Slick water, tagged with a naphthalene disulfonate, and I'd have to look up specifically which one, but in each of the 3 stages that were pumped, it was a different species of tag. The second, we moved up the hole, in a cased and perforated zone, we pumped slick water, tagged fracture. The third stage, we moved up the hole a little further and we pumped a cross-linked carboxymethyl hydroxypropyl guar, once again with a tag. So just run through it briefly, just so that you have a feel for what's going on. So remember, stage 1 was open hole, pumped at a maximum rate shown in this greenish, in this lime, at 50 barrels a minute. The rate scale is to the right. So we're at maximum 50 barrels per minute. And surface pressure is shown at the left. And this was pretty flat profile, relatively independent of rate after opening had occurred. We flowed that well back for a substantial period of time. Surface temperature of about 222 degrees Fahrenheit. Subsequently, after 16 hours of flow back, we ran into the hole with a bridge plug. And historically, we've had significant difficulty in coming up with isolation technologies such as bridge plugs. In fact, a frac plug would be desirable. A frac plug that could be run on wireline, even more desirable. But those were not commercially available or viable at the time. So we ran a bridge plug, and the setting tool for the bridge plug required a rig. So we had a rig. You can see the bridge plugs at the bottom. Interwell, Norwegian company, really worked with us in a very collaborative manner, and these tools worked extremely well. You can see the elastomer that provided the seal. So we ran the bridge plug in the hole, set the bridge plug, we tested the bridge plug to a differential pressure of 7,000 PSI. Then we ran in the hole with a perforating gun, 20-foot gun, single cluster, a long gun, so that we'd be sure that we would intersect some sort of pre-existing weakness. 6 shots per foot, 60-degree phasing, 21-gram charges. Everything fired. So we have a perforated zone with a bridge plug below it. We pumped about 2,800 barrels of slick water and flowed back for 12 hours. So you can see that in the cased and perforated scenario, there's a slightly different pressure profile, a declining pressure profile as growth occurred, as opposed to the flat pressure profile in the open hole where presumably multiple fractures were taking fluid. So after that's done, flowed it back, set another bridge plug, and went on to pump stage 3. And stage 3 was the viscosified fluid with a little bit of microproppant, very small concentration, small amount. Microproppant is sub 300 mesh proppant, and pumped 3,000 barrels of that and flowed the well back. Profiles somewhat similar. So all of this is just setting the stage for the circulation testing that we did after we had drilled 16B. The purpose of the circulation testing was to establish the degree of connection between the 2 wells. One of the things that was particularly interesting that Clay Jones and Stuart Simmons and others found was that the flowback water after the fracs in the 16A well in April 2022 contained high quantities of chlorides. There were indications in the figure at the right that there was no interaction between the fracture stages, that the tracers pumped in one stage were not detected in the next stage if they were isolated. And so we can go into this illustration, but I think the bottom line message for that is that the fractures were discrete. There was not an interaction between the fractures. However, the surprising thing from the flowback were the salinities and the TDS, and this in turn, these chlorides in turn turn out to be a very nice geochemical signature for new fracturing being created in the reservoir. So the other thing, as I mentioned, and this is one of the important things, is that we had up to 3 geophones functional in multiple wells, and we were monitoring the microseismicity that went on. And if we go to start from the upper left, and we can see stage 1, open hole, relatively weak signals, and this may be an outdated version. There may be more events that have been detected, and some of the locations are, I won't say compromised, but are difficult because there was only 1 geophone functional. So if the blue is the injection well, the gray is the injection zone, and what you can see is not a great deal of activity in the injection zone, and that could be, and lately we've got more events showing up here, but very small. So this could either be a function of Kaiser effect because we had pumped into this zone previously, or the fact that there were multiple entry points where the velocity was relatively low and the magnitude events occurred were not significant. But later in the injection program, we saw events that grew back at an angle towards the well, and my interpretation of that is that the velocities became low enough that fluid started to go into pre-existing natural fractures. It followed that were not necessarily vertical, and hence you see the inclination. The second zone, as you recall, was cased and perforated. And let me just mention that the magenta line is our perception of where the 16B well was drilled, plus or minus. It's pretty close. This is 300 feet separation. The second zone, slick water pumped at 35 barrels per minute, was a relatively vertical, maybe slightly inclined, maybe slightly diffuse, seeing some natural fracture. But once again, we didn't have complete geophone coverage, but we had better coverage than stage 1. And we definitely saw events that were growing more than 300 feet vertically. The third zone was the viscosified fluid, relatively planar, some interesting bifurcations on it, and definitely the microseismic cloud was more than 300 feet vertically above the injection well. Now, as we all know, is that just because you have a microseismic cloud does not mean you have a distinct hydraulically connected fracture, that there can be dry versus wet events. And indeed, I think this was supported by some of the things that we saw in the circulation testing. Nevertheless, if you look at all of the 3 stages together in the bottom 2 views, you can see just an outstanding profile of the seismic events. A lot of credit here to Geoenergy Suisse for all of the efforts they put into this beautiful, beautiful catalog. Now, the bottom line, though, is that from this, we saw no indication that we should not drill 300 feet above the wells, that would look like it would intersect the microseismic clouds that are being created. So we went ahead and we drilled the well, as I described earlier, and then we carried out circulation testing. And there were 2 campaigns that were carried out. One was in an open hole setting before we ran the 7-inch casing. So that was run on July 4th and July 5th of this year. We ran that at rates between 1/2 and 7.5 barrels per minute in stages, and I'll show you that in a minute. And the open hole section went from the bottom of the 11 3/4 inch casing shoe to the drilled TD of the well. So from 4,837 feet, that'd be in part of the vertical hole, to the toe of the well at 10,947 feet at a 65-degree inclination. So if we start from the illustrations in the upper left, you can see that we had Schlumberger brought in 2, and we can only see one of them in these pictures, coil tubing pumping units. And the purpose for these coil tube pumping units is that we could control the injection rate and provide the pressure at low enough injection rates where we would not be creating new fractures. So we had 2 of those units. So starting from the upper right and moving counterclockwise, there's one of the pumping units. You can barely see the iron and the wellhead that it was hooked up to, and on the right you can see frac tanks. At the upper left, you can see some of the instrumentation that was designed by Kevin England and by Rob Podgorny, and this is monitoring off of the 16B wellhead. Then at the lower left, you can see a tan Connex that served as a separator. So this we custom built a separator out of a Connex with baffles and holes in the top, and installed that. And what you can see here is you can see the line going into the Connex and a throttling valve that would allow us to control the flow that would go into that well, so that we could maintain a back pressure. Bottom right is the outlet from the separator. We have 2 lines, one primary line and one line in case the flow got large enough. So what happened on this open hole section? Okay, so let's look at this. Let's look at this plot from July 4th. What you've got is you've got red showing the injection rate, and the vertical scale for the injection rate is in barrels per minute, and it's on the right. And you've got blue showing the surface pressure. So we have not yet converted these to bottom hole pressure. That will come, and a great deal of analysis yet, but nevertheless. So you can see that starting out at 1/2 barrel per minute, very little activity. Pressure just sort of leveled out. So following the protocol, we increased to 2.5 barrels per minute. Once we got to 2.5 barrels per minute circulating, bullheading fluid down the 16A well. So that's going into 3 previously fracked zones, an open hole 200-foot zone that had been fracked, and 2 cased and perforated zones that had also been fracked. And the fluid was just bullheaded down, no isolation. And increased to 2.5 barrels per minute. Once we got to 2.5 barrels per minute, things sort of caught and pressure built, and eventually you started to see some sort of opening somewhere around in here. So the 2.5 barrel per minute stage went fine. Some difficulties with the pumping equipment. As a matter of fact, we shut in to bring on a second pump, and eventually pumped 5 barrels a minute. And at least for the first part, there's a characteristic pressure drop that occurred during the circulation testing. So what happened? That's at the 16A well. What happened at the 16B well? Well, this is going on, and I've approximately, or pretty closely, I think, lined up the times here, so you can see that really nothing, no significant level of communication at 1/2 barrel a minute. At 2.5 barrels per minute, we started to see pressure catching in the 16B well. So the throttling valve was closed, and we kept this, so that prevented fluid from going to the separator. So that meant that we had a closed system that we were pumping into. So the pressure built, and at 2.5 barrels per minute, it built relatively rapidly, and continued to build at the 5 barrels a minute. Once we got to 200 PSI, as per our program, we manually adjusted the throttling valve to keep the back pressure at 200 PSI. and see what sort of flow we would get. Insignificant flow or small flow, so we dropped it to 100 psi before we shut in for the night. And however, we were seeing a pressure signature, and when we shut in, the pressure built rapidly, and stabilized overnight, I think at about 500 psi. So the next day, July 5th, after the fireworks, we resumed pumping, but this time the pumping was pumping at 5 barrels per minute for the entire day. And a couple of interesting things here. Okay, first of all, the pressure didn't build to the 4,500. It just started off about where we left off at 5 barrels per minute the previous day, and the pressure dropped a little bit further. And so, you know, this is one of the things that one can speculate about why this was happening, whether it was thermal effects, some sort of something in the cool down, hydrostatic head in the pipe that you filled up previously created fracture networks, et cetera, et cetera. Nevertheless, it did remain constant. Now, we had flow meters in line to measure flow, but their threshold lower limit was a barrel per minute, and we were not getting that. So we did 5-gallon bucket tests. And as the day went on, as you can see in the lower right, the rate progressively increased steadily towards about 15 barrels per hour. And so a definite establishment of connection in terms of flow, in terms of pressure response. We've also measured increases in chlorides as we circulated fluid, bottoms up fluid after these tests. And the chlorides, as you recall from the previous flowback work, we're taking those as a signature of fracturing, new fracture surface having occurred. We were also monitoring for tracers, but I think, and we have found tracers, but we're just not ready to release that data yet. We just need to QC it a little bit further. So that was in the open hole. So then we cased the hole, ran the fiber optics, and repeated testing on July 18th through 20th. And what you can see at the right here, we modified the setup a bit. We had less equipment on location because the casing was gone and things like that. And so there is more room to work here. And so what you can see is that there's a lot of instrumentation that was along here. Flow meters, pressure devices. This is the throttling valve that would regulate flow to the separator. And this is downstream of the separator where we would have measurement devices there. Once again, we followed a program of rates from 2.5 to 7.5 barrels per minute, but this time it was in a cased hole. And the cased hole was covering at least stage 3 frac previously, and possibly part of stage 2. It's hard to say. The casing went to 10,208 feet. So that left about 739 feet. Is that right? Yeah, 739 feet of hole or something like that open. So we could at least look at stage 2 and stage 1. Schlumberger brought in a different set of equipment just so that we could get the 7.5 barrels per minute here. We pumped it 5 barrels per minute previously. I might have said 7.5, but it was 5. Or I believe it was 5. Pumping units you can see at the left, and you can see iron going to the wellhead, and that was sort of the pumping configuration. At the right, for the second 2 days, and it just straddled midnight. That's why it was 2 days. We ran a spinner survey, a pressure temperature spinner survey in the 16A well while we were injecting. So we would be moving this spinner device up and down the hole, not into the open hole section, but below stage 2 and above stage 3. So we were, and between stage 2 and stage 3. So we were able to partition the amount of flow going into each one of the zones as we carried this out, and some interesting data there that what bears a lot of further evaluation from a modeling perspective. So this is 16B is now cased. We're injecting into 16A, and this is sort of what we saw. So here's the first day. No spinner survey this day. We once again, the blue is surface pressure axis to the left. The red is treating rate axis to the right. And you can see we started at 2.5 barrels and we went to 5 barrels and we worked our way up to 7.5 barrels a minute. And so you can see once again the rollover at the 2.5 barrel per minute rate, followed by a pressure drop, you know, and once again, some evaluation here. There's a number of possibilities. We were trying not to grow new fractures. That's why we're trying to keep the rates low. Can't rule it out completely. That's at 16A, and the 16A pressure curve is repeated in the bottom panel, and we're also showing 16B response. So initially we were allowing the pressure to build up. We were holding 200 psi back pressure, holding 200 psi back pressure, dropped it to 100, then went to AOF. So just open flow completely, and repeated that. But ultimately, then we left it open to flow continuously, and it did flow continuously. There were a couple of times we shut in and recycled just to see if there were any sort of events that occurred there. Then at the end of the day, we shut down. When we shut down, we were going to maintain the pressure at 500 psi, but it quickly got away from us, and the pressure built to 1,000. This pressure would build substantially. That's the other thing to mention, is that between these two circulation tests, one ending July 5th and one starting July, what was it, 18th, both wells were shut in, or the 16A well was shut in at least, and the 16A well held pressure. When at the end of this, I don't know, 10-day period, there was still 1,000 psi on the 16A well. So it suggests that this is a container, and that there is a weak communication between the two wells, but it still needs to be developed further. So that's the first day after the casing had been circulation after casing had been cemented in place. The second day we ran the spinner survey, and so we moved the spinner, started at above stage 3, moved it to between stage 2 and stage 3, moved it below stage 2, and so anything below going below stage 2 is going into the open hole. And so we were able to discriminate between all 3 zones, and we did that at 2.5 barrels a minute, 5 barrels a minute, 7.5 barrels per minute, moving up and down, and allowing the flow to stabilize at each point here. A grease seal had to be replaced here, and that's why there was that shut-in. And so now you can see that there's more and more ready communication and rapid interaction between the two wells. The blue being what happened at 16B, that it would build almost instantaneously. We would hold it at 200 psi, hold it at 100 psi. But there was a much more significant communication occurring. So previously I showed data from Nubrix. Also, we have great data that's being evaluated from Silixa, and this is just an illustration of some temperature data that is being interpreted further. There's also a very nice microseismic event that Joseph Wolpert pointed out to me, recorded by their DAS. And so a lot a lot of fiber data during the cementing and during the circulation testing that bears evaluation in the near future. in terms of the flow from the circulation, once again, you can see that the blue curve indicates surface pressure at 16A. The red is the injection rate, and the dots are flow rate measurements. And you can see a progressive increase up to about what we saw before, about 16 barrels per minute. Now, and then we're getting close to wrapping up here. And I've gone long, I'm sorry. This is showing the flow rate data for each injection rate. The blue is 2.5 barrels per minute. I guess is brown is 5 barrels per minute, and the gray is 7.5 barrels per minute. And so you can see that the stage 1, which is the open hole section, took a fair bit of fluid, and that's expected because it's 200 feet long compared to the other zones, which are shorter. One of the perforated zones did not take very much fluid. That was the slick water frac, and that's probably because the width is not well. I mean, I don't know. I'm not sure I know the answer to that, but it took less fluid. And stage 3 being closer to the injection point, maybe that's just why it took more than stage 2, as expected. So once again, fantastic information. Thank you to Schlumberger for really helping out with that data. So if we look at some of the stuff and we start to draw conclusions, we see that significant injection required pressures that were above the minimum principal stress. The connection was definitively established, but needs to be improved. By virtue of holding pressure over a week or so, we can see we're fracturing an anomaly impermeable domain, and we have a highly conductive network to what we think is relatively close to the 16B well, with what I'm calling a ligament of lower hydraulic conductivity that will need to be improved by pumping either larger fracs, pumping proppant, reworking. And a lot of credit here to Peter, discussions with Peter Meyer from Geoenergy Suisse for putting forward some of these concepts. So you can see that the initial cycles showed a pressure decline, and maybe that's something that bears some consideration. Proppant is going to be a prerequisite for the future, likely larger volume stages as one would expect. We'll be able to use the fiber optics, and we're fantastically appreciative to all of the parties, particularly Alan Reynolds, working with his colleagues at Shell and UT for getting all of those fibers run effectively. So as we suspect, microseismicity overestimates the fracture domain. You're seeing a cloud, you're not seeing a direct communication. And having the fiber in place will help with future stimulations so that we can ensure that that we can correlate between the microseismic network and effective communication. And then ultimately, we're probably going to have to do something at 16B to facilitate overcoming the near well restrictions. So all in all, just a fantastic test, very, very successful. Connectivity established and just on schedule. I mean, this is what we've been talking about. The next stage is conductivity, and then subsequently looking at conformance and long-term circulation. So I've run long, I apologize, but I really want to thank everybody that was out there on this well for making it a real success.
John, you have some questions in the chat. Would you like to address them?
So Luke, the two reasons is well, so I'm going from the bottom. Is my estimate correct that peak recovery? Did you observe microseismicity? Some limited microseismicity was observed, Luke. Yes, and so the recovery is requires improvement. And this is anticipated, but you have a connection. You're not pumping proppant. You're not pumping large jobs. And I think people have been advocating that we need to pump more fluid and more proppant. The production well was cased for primarily so that we could run fiber behind it and understand the fracture geometry. It's also run, and there tends to be disagreements here. It's also run so that you can see where the fractures are hitting, and you can subsequently perforate and hopefully not damage the cable and establish a connection. I think that what we see certainly from the injection well and the open hole section is that the open hole section is showing relatively weak seismicity. Probably multiple fractures being generated that really do not have a significant amount of hydraulic conductivity. And so I think that there really remains an argument in the community why one cases the production well. But certainly in this case, it is for running fibers, and so that we can manipulate where fractures are growing, and also where fractures are producing from. Is the ideal in the future, and that may in the future require sliding sleeves rather than a cased and perforated completion. How much? Yeah. So as Luke pointed out, there was a relatively small interconnection between the two wells, and we did not pump enough fluid to bring fluid to the surface, but we circulated fluid out, and we found tracers and an elevated chloride content in the fluid that we've circulated out. So, this is why we're suggesting that there's a high hydraulic conductivity up to a relatively short distance from the injection well, and then there is some sort of I hate to use the word skin, but that's almost what it looks like. It's not. It's a mechanical skin rather than a damaged skin. Yes, and Ahmed, yes, we did inject above the minimum principal stress. The minimum principal stress is somewhere in the neighborhood of 0.74 psi per foot. Our experience here is that, and certainly my bias, I have to admit, is that you have to create these fractures and to communicate these fractures, you have to inject above the minimum principal stress. In a production scenario, I also advocate that you have to have conductive pathways that are preserved by having proppant, so that you do not have to have a back pressure that exceeds the minimum principal stress. That you just need to overcome the hydrostatic head and possibly rely on a little bit of thermosiphoning so that your parasitic losses are reduced. So great questions. I mean, and I don't necessarily have the answers to all of these. I mean, Luke's question is an important one. Do we case the production well? Well, in this case, we definitely case the production well for fibers and also to allow us to control future operations. Yeah.
There's another from McCall, and Luke, if you have a conversation, maybe you can just come on and ask.
I think McCool's question was answered. It was like 5%. And Luke, yes. So the plan for the future is additional stimulation in 16A, and then going into and this is John talking. Okay, it's not being validated and approved. But you go into 16A with a number of frac stages, and our concept at the present time is we want to look at a couple of things. We'd like to take advantage of 16 stage 3 and possibly refrac stage 3 with proppant. We would like to look at proppant with slick water and proppant with a viscosified fluid, and we would like to look at least one stage with multiple clusters. And that would be in 16A. all of these would be within a zone that would be monitored by the fiber optics. Then we would go in and we have to orient the fibers. We have to log the fibers to determine their orientation, and potentially, and at some time we will have to perforate 16B to develop some sort of connection and circulation. Water jetting is not out of the question in the casing. In the case of of fibers in place behind the casing, I think we would rather try oriented perforating. Water jetting is always a consideration if you're not worried about cutting through fibers.
John, can I ask a question about the produced water in the 16B well? Only 5% of the water was produced. Could you speculate on where the other 95% went?
No.
I mean, it's an impermeable formation, so it must have gone somewhere.
Yeah, and this is a very relevant question, Mukul. Unless one of the possibilities was that we were flowing back and every day we would have to recharge the reservoir, and there was some loss, possibly some new fracture being created, although we were trying to pump at a rate low enough where that wasn't the case. But this is something that I think this is something that I think modeling is going to be able to help us with, quite frankly.
To me, that's the most surprising result, is that you're injecting fluid and it's disappearing into who knows where.
Yeah, precisely. So it is a bit of a conundrum. What is the effective injection pressure you found necessary to overcome? It's about 3,000 psi at the surface. So in bottom hole, it's going to be 0.74 to 0.78 psi per foot. Oh, look, not a question. Oh man, I must be losing my touch. Rob mentioned pressure gauges in other wells. Where no, and we have not Jonathan. We have not processed that information, but just looking at it, I mean, it was on the screen while we were pumping. We saw no indication that there was any sort of communication in the far field. One of the things that is really fantastic and has impressed me in terms of pressure gauges is now we do have a downhole fiber optics pressure temperature gauge. It's installed just below the heel, and that, at first I wasn't, I didn't really see the value of it, but we actually ran a test using that device where we swabbed the well. We knew how much fluid we took out, and we measured the pressure as a function of time as that recovered. So kind of a production build-up test. And so I think really I'm now a convert for that. Yeah, so look, there are some similarities, I think, to what you saw at CoLab, and I think that the opportunity now is to figure out how to improve that connection, and really to answer Mukul's question is where exactly is that fluid going, and how can we encourage that break down that ligament, and I hate to call it skin, but I think we could call it a skin. That's existing around the 16B well.
Yeah, because the volume of fluid that disappeared, John, was actually quite substantial. I mean, it's probably quite a bit more than you would accommodate in a fracture, wouldn't you say?
Well, I think that this goes to play that life is there's a lot of gray in life, and that what you probably got is you've probably got ultimately a very, very tight, and once again I'm speculating, a very, very tight reservoir, but the natural fractures are being inflated via pressure dependent leak off, quote unquote, I mean, using that analogy, and that you have a tree trunk that's an extensional major pathway, but as you are reinflating and you're filling up a significant natural fracture network. Now, the thing that surprises me about that and belies that, and so maybe they're parallel fractures, is that in the initial frac work, we did not see any tracer interaction between the wells.
Mm.
And so it's not like it's just a big old oak tree growing out. It's maybe a tall poplar or something like that.
It's those dead end fractures and that we have from our results in the modeling.
I think I would agree with that, there are dead end fractures. And so, one needs to ask the question is that if you're getting those, what do you do about them? Because they're not doing you any good.
I agree.
In the circulation scenario.
Yeah, I agree. So I think it's a very important result actually to try to figure out where that fluid is going, because if you have the situation continuing for any extended period of time, it's going to really play havoc with the energy recovery.
Oh, well, I'm less worried about the energy recovery than just the inefficiency of the treatment.
Well, both really. Yeah, both.
Yeah.
So John, I can add a couple of comments maybe to help on Nicole's
Please.
question about the fluid volume.
Yes, please.
So no, remember, pumping the 3 frac stages originally we pumped, I'm just going to use round numbers. I don't remember exactly, 10,000 barrels of fluid, of which we flowed back about 5,000. We got about half of each stage flowed back every time we flowed back in between stages to set the plugs and do the subsequent stage. So, presumably there's, still 5,000 barrels of fluid in there somewhere from April 2022. And there's going to be some bits of leak off and stuff, obviously, into the formation through the surface area of all the fractures that are exposed to the rock. But now we come, to do the circulation test this much later. And in any individual circulation test, we pump 2,000 barrels of fluid, right? So you're not even refilling the volume that you flowed back from the original fracs, or not even close, when you pump the circulation test. And unfortunately, we had to, flow back a little bit during the circulation test to accommodate running the PLT and stuff like that. So, I think where the fluid went, if you look at material balance, is the fluid went back where the fluid was when we did the initial fracs with 10,000 barrels, and we never really refilled that volume.
Good point. That's a really good point, Kevin. The other thing is that steam is quite compressible. So as you increase the pressure, you might actually be recondensing some of it, perhaps, but I mean it's still going to be steam, but it's quite compressible.
Yeah, and I always we forget that when we're injecting the circulation test, we're pumping back into all 3 of the stages, and we saw the distribution at least on one day, of pumping from the PLT, but. That even goes back further, if you just apply that, again, back to the material balance, looking at all the stuff you pumped in, everything you flowed back and then pumped back in, I think that we'll definitely find that the volume that we pump back in during the circulation test still doesn't exceed the original volume again. And that also kind of explains a little bit maybe the choke effect at 16B, because not really sure we opened the fracture all the way there enough to have any, major connectivity to establish a really good circulation rate.
Yeah, I hadn't done the calculation of how much fluid you had injected during circulation, but you're saying that's quite a bit less than the volume that you pumped during fracking, is what you're saying.
Yeah,
that's an important number then to
yeah, all the circulation tests. So you look at all the circulation tests added together. I think I'm getting this right, but then we pumped about 2,000 barrels each one. So that's 8,000 barrels compared to 10,000 barrels we did for the total frac. So
that would be an important number to keep in mind, is how much total fluid was injected during circulation tests.
Yeah, and that was one of the things we talked about before the circulation test design was, the question about however the distribution went into the different stages, would we pump enough fluid into even one of the stages to get everything opened up from A to B.
Mm-hmm.
And let me just answer one more question. Hello, Marty. Yes, we ran a bond log in the vertical section. And we couldn't get a high temperature bond log immediately. So we're planning on running one within the next couple of weeks to do an evaluation on the entire length. So that's all I know.
Great talk, John. Thank you.
And if anybody's got any questions or recommendations, please drop me a note and copy Kevin England if you have his email.
Okay, that's a wrap.
Okay, thanks all.